Hi everyone, my name's Will. I hope you all are doing well, and here's my project on the physics of water polo. So the first concept I want to discuss is density. And so basically, our equation for density that we have is the mass of an object divided by its volume. And we know as a standard that the density of water is 1 gram per centimeter cubed. And so density relates to water polo because as humans, we are very dense. So we sink in water unless we're held enough up by a great enough upward force, which counteracts the downward forces on us. And for the case of water polo players, to do that, we just tread water or we're swimming on the surface, and that allows us to stay up on the water and counteract those downward forces acting on us. And compared to the average person, most water polo players are more dense due to their larger than average size, and they also have larger muscle mass in order to deal with the physical nature of playing water polo. And to reduce density, water polo players do such things, including wearing a cap, shaving their bodies of hair which would create drag, staying in tip-top shape by constantly swimming and working out, and wearing a Speedo in the water in order to reduce the amount of cloth drag that would come from, say, swim trunks or a bathing suit. And since many players cannot change their mass, the only way that they can really reduce their density outside of the ways that I mentioned is by increasing their volume, which they can do through efficient swim strokes and maximizing a player's surface area in order to combat their mass and spread it out in order to increase their density. And so if we look at these pictures, we can see on the one to the left that the guy is maximizing his surface area in order to stay on the surface and spread out his mass and decrease his density. And on the right, we have the woman who is using those efficient swim strokes to help keep her upper torso out of the water and create enough upward force to counteract the downward forces that are pushing on her from her density and from gravity. The next concept I want to discuss is buoyancy. And buoyancy is the loss of weight experienced by submerged objects. And the upward force of a submerged object is equal to the volume of water that object displaces. And buoyancy relates to water polo because, for example, we can take a standard water polo ball, which weighs an average of 450 grams, and then we can find its circumference, which is 71 centimeters. And if we take both of these metrics, we can calculate its density. And the density of a water polo ball is around 0.009 grams per centimeter cubed. Now, if we remember that the density of water is 1 gram per centimeter cubed, we can see that the density of the water polo ball is much less. So, therefore, it requires a lot of downward force to push the ball under the water, which allows it to float easily on the surface. And when a water polo player is directly on the surface, when they're swimming or floating or doing anything of that sort, the only downward force that's on them at that point is gravity because their density is being counteracted by the upward force of buoyancy. So that is when speed and movement are most optimal for the player. So when the more of a person's body that's underwater, then it feels more downward force from its increased density. So based on buoyant force, you want to spend as much time on the surface as possible in order to have more upward force pushing against you and to not require you to use more force to fight against the downward forces of the water. And some examples of buoyancy here is we have the water polo ball floating on the surface due to its greater upward force than the downward forces of density and gravity. And then in the picture to the right, we have a player who is using downward force to push the ball down and counteract its upward force, which makes the ball sink into the water and allows for this picture to be taken. The third concept I want to discuss is projectile motion. And the basics of projectile motion are that a projectile is any object that moves through the air, and it's only acted upon by gravity and air resistance while it's in the air. And projectiles take the flight path of a parabola, which kind of looks like a U, and it has optimal launch angles of 25 to 34 degrees in order to maximize the distance of the projectile. So if we talk about water polo, we can consider that the ball is itself a projectile, but it's subjected to much different conditions than most projectiles due to the nature of water polo. So when shooting, a player raises his body as high out of the water as possible so that he, when he throws the ball, can launch the ball at a downward angle in order to score. This gives the ball, supplanted with the large force of the player going up and pushing downward on the ball, a high velocity, and gives it a straight path, more like a vector that we see when we calculate the path of the parabola. But if we look at the ball when it skips off the water, the ball takes a parabolic path, which demonstrates the effects of projectile motion on the water polo ball, as it is a projectile and is subjected to gravity and air resistance, just like projectile motion suggests. And so if we look at these pictures, we can see on the left we have a picture showing the projectile motion of a ball when you throw a lob. And the second picture here is to demonstrate how players use their downward force in order to shoot the ball. The next concept I want to discuss is momentum. So when we think about momentum, you think P equals mv, and that just means that the momentum is the mass times the velocity of the object. And in simple terms, momentum is inertia at motion. So we know that if an object's at rest, it doesn't have any momentum. So if we talk about water polo and momentum, both the players and the ball seemingly have a constant momentum due to the waves of the water, which technically means that players are never at rest during a game because the waves will always cause them to have momentum. And because momentum cannot be canceled, it can't be destroyed is the better term. The water cancels out the momentum of the players and the ball constantly during the game. So instead of momentum being destroyed, the momentum is dispersed into the water. So this follows in the conservation of momentum. And so the more speed a player puts on the ball, the faster it will go, and the more momentum it will have due to this increased velocity, since you can't change the mass of the ball. And the same goes for swimming, too. If you increase momentum, you'll swim faster. And so here we have the skip shot, which is a perfect example of momentum, as because of its mass and velocity, even though it hits the ball hits the water and disperses the momentum, the ball keeps going because that momentum is great and it's not enough to be dispersed completely by the water. And the conservation of momentum tells us that the momentum will keep going until it is sort of canceled or equaled out. The next concept I want to discuss is a Newton law, specifically the third law, which is that every action has an equal and opposite reaction. So there are many different aspects where Newton's third law relates to water polo. And the focus here, because there's so many of them, I want to focus on treading water, which we water polo players call egg beater. So when a person does not apply force in the water, they begin to sink to the bottom of the pool due to the downward force of gravity and the density of our bodies, which I was talking about earlier. But that force can be canceled if a swimmer pushes upward with an equal force to the one pushing down, which can be done through pushing upward with one's legs, creating enough upward force to cancel the downward force of gravity and density. And so this force can be sustained through moving one's legs in a constant motion, which creates a vortex force which cancels out the downward forces on a person and allows for one to tread water. So if we think back to Newton's law, every action has an equal and opposite reaction. So as our bodies counteract us with gravity, the force of gravity and the force of density, we can have an equal and opposite reaction to those forces by moving our legs in egg beater form to create a vortex. And it's easier to show through a video, but I'm going to use pictures. And so we see on the left is the form for egg beater. So we can see by circularly rotating the person's legs that they will be able to counteract the downward forces on them and create constant motion, which will continually have an equal and opposite reaction to those downward forces. And then on the right is just an example of egg beater being used, and you can see that egg beater can create very high upward forces as this player gets his whole upper body out of the water, as you can clearly see that his speedo is coming out of the water in his efforts to block the ball. The next concept I want to discuss is inelastic collisions. So you usually think oh, I don't really think about many inelastic collisions, but water polo shows constant inelastic collisions. So if we consider that inelastic collisions are colliding objects that become distorted, generate heat, or stick together due to the collision, then we can see that inelastic collisions relate to water polo. Because when we swim through the water, that is technically our bodies colliding with the water and distorting it by creating waves and splashes which disperse the water. And so while the player's momentum moves in one direction in the collision, the momentum that goes through the water is dispersed all around instead of being counteracted directly back in order to conserve momentum. So instead of being conserved directly and equally opposite, it's conserved by dispersing itself. And we can also think that the water sticks to the player, which we know is because when players get out of the pool, they're obviously wet, so they have water on them from the pool, which means that the pool water has stuck to their skin. So if we classify water as an object technically for the purpose of our collision, then water sticks together with the other object, the player. So this would create two ways in which players colliding with water is an inelastic collision. And so obviously some examples of that are both this player taking strokes. You can see all of the white water around him, which are examples of constant inelastic collisions. And then I decided to bring up the ball too, because instead of the player, the ball could be substituted as an object. And when the ball hits the water and creates splashes, that is also an inelastic collision, which references back to when I was talking about the water polo ball and momentum earlier in this presentation. And the last concept I'm going to discuss in my presentation is water's high specific heat capacity. So to change the temperature of 1 gram of water by 1 degree Celsius, it takes 4.18 joules of energy, which is a higher heat capacity than all but a few uncommon materials. And water interacts with the surrounding environment as it cools the hot air that is around us in the summer, and it warms the cold air in the winter. So from my experience with water polo, if you're the last team to use an outdoor pool in the day during the winter and spring, you have to cover the entire pool with tarps, which is a very painful process, especially if you're doing it at 9 o'clock when it's very cold outside and you can feel the steam coming off of your body and your water because the water is warming the cold air that is hitting your body. So it also explains why the pool stays warm. So when you put tarps on the pool, that is to make the pool stay warm, because water has such a high specific heat capacity and it requires so much energy to heat water that it's very hard to heat it efficiently. So it allows people who operate pools to save money, heat, which are all valuable resources, and saves money, which is the bottom line for managing a pool. And so this also explains how the pool feels to players. So when we hop in the pool in the winter, it feels pretty warm. It feels pretty good to go in the pool. And then when you get out, it feels super cold. And you're like, geez, that's very cold. And then in the summer, when you're boiling outside because it's super hot, you jump in the pool and like, oh, this is so refreshing. And that is because of the properties that water has due to its high specific heat capacity. And so here is an example of a pool that is being tarped in order to keep its warmth. And then this pool is then removed their tarps, and you can see the steam coming off the pool as the water warms the cold air around it. And that concludes my presentation. So thank you very much for listening, and I wish you all the best, and hopefully I will see you soon.